Hello everyone, this is Team 18 and the name of our language is JAL, just another language. In this video, we'll go through the various features, syntax, grammar, intermediate code and runtime of our language. Our language is a functional and statically typed language. We have taken inspiration from C. We perform lazy evaluation and use static scoping in our language. This is our syntax. For variable declaration, we have type specifier and identifier. For function, we use func keyword. We don't use curly braces for blocks and instead use end func keyword. Similarly, in if-else and while statements, we are using end while and end if statements to define the blocks. To generate the intermediate code, we use Antler. For this, we first create the grammar in a .g4 file. Then we use Antler to generate the parser, lexer, and additionally the visitor class. Antler prepares us with a set of functions to visit the nodes of the parse tree, and then we can return the user-defined operations for them. Additionally, it provides us with some functions such as visit children, get child count, aggregate results, which we have used in our implementation. This is a snapshot of our grammar. A program can either be a statement or a function. A statement can either be a declaration, an assignment, a branch operation, or a stack operation. Expressions are also written in such a way to maintain the precedence. We have also added features to get the parameter count when working with functions. This is a sample syntax tree that is generated using Antler. It defines an arithmetic operation. As you can see, there is precedence maintained between the multiplication and the addition operation. Our intermediate code is composed of several opcodes which make it easy for runtime execution. For addition, multiplication, division and subtraction, we use push command to push both the operands onto the stack and then perform the operation. The load and store commands are used to move the variables between the symbol table and the stack. Let us now look at some sample intermediate code. In the first example, we are assigning the value 10 to A. So we push 10 onto the stack and then store the value of A as 10 in the symbol table. For the second example, we first load values of A and B from symbol table and then store it to C. The third example shows how precedence is followed for arithmetic operations. For if-else statement, we maintain labels. Labels mark which statements are to be executed if the condition is met. Additionally, we have a unique identifier which basically helps us to differentiate each if-else statement. This enables us to have nested if-else statements. For functions, we have the start and end tags. We also specify the number of arguments. This helps us to retain the correct number of arguments when the function is invoked. The return keyword simply returns the top of the stack. One can generate the intermediate code using the command as shown here. The generated intermediate code can now be fed into the runtime for execution.
So let us look at the runtime now. We will first look at the runtime for conditional statements. Conditional statements are implemented in JAL through if-else constructs. JAL also supports nested if-else using unique identifiers. Here is a function named max which returns largest of the two numbers passed to it. So now let us run a sample program for if-else functionality. So this is our sample program which has nested if-else functionality. To compile the program, we will run through our command which is java jar compiler.jar. So we'll compile through this our compile.jar and we'll just pass the file name. So the file name is nested if. So if you can see, we have all the programs here and we have a nested if JAL here, but we don't have a class file for it here. So when we compile it here, we get a class file for this JAL file. Now we just need to run this JAL file through our runtime and we pass the class file here. So we get result at 16, 86 and 41. So let us check the correctness of this program and result. So in this bytecode, the conditions are evaluated here, and if the condition is true, then we use the if true label to execute the statements, and if the condition is false, we go to the if not true label. So this one. So this is the if not true label for the nested if, and this is the if true label for the nested if. So the identifier can also be seen here with the labels, if you can see that. So we have if true 1, so which is the label which uniquely identifies which nested loop you are in. So now let us go back to the next part. So we have a loop constructs in JAL2. The loop control in shell is implemented through while loop. So functionality same as in other languages. You can see the sample program here, just sum, and which in the while loop as well we use the labels to iterate over the same part of the program as long as the condition is met. So let us have a sample program for that too. So this is our sample program for while. We can just compile it with the same commands we used for the if thing. So we have a while program here, and again you can see that we don't have a class file here. So as soon as we compile this gel file, we will get the class file for this. So yes, we have the class file. Now we just need to run it with our runtime. So we'll just pass it the class file to this command, and you can see the 55. So we pass 10 here, so it gives us the result as the sum of first 10 natural numbers. So now let us look at the next functionality. So next we have stack, which is implemented by the stack. It does stack ADT, and which performs function like push, pop, peek, and the size. And let us see a sample program. So here we have a sample program for stack, which pushes some element and then pops and prints it with the top element. So we'll just compile it with our compiler. So here it is, the class file, and then we'll just run the stack class here. So we get the results at 30, 20, which were the desired results. So let us move on to the next functionality.
For runtime function part, if the execution for each command works well, include assignment statement, if then else construct, and while loop, then there are only several points we need to pay attention. The first one is the scope problem. If we cannot access variables from other functions, so we need to create a symbol table for each function, and for each command, the execution will be based on the symbol table we pass into. This is the code. All the commands executed inside the function were based on this local symbol table, so that we can solve the scope problem. The second problem is how to organize the index when you encounter a function, like the program counter inside the CPU. When you execute a function, you must need to jump into the body of the function. The function body start line always different with the line you call the function, and we also need to manage how to continue executing the rest part when the function over. We need to come back to where we enter the function. The method is to mark the line where you call the function and give it back when the function ends. And also there is a pre-treatment that can save you time. You can scan the whole file and put the function start line number into the hash map that you can find them quickly in the runtime. Okay, let's talk about the example. The first one is the example about the scope, the different value of variables in different functions. And the second one is the factorial. We solve the factorial by using the recursion. Okay, let's go. I just prepared the command because it saves time, and also those two are our source code. This one is for the intermediate code, this one is for the runtime. Okay, let's do it. First one is to get the intermediate code. You can see that. This one is for the runtime. You can get the answer. The same with the second one. Get the intermediate code and just get the answer. Okay, thanks for watching.